So I wanted to go through number 6 and 7 on the worksheet that we did today to review for our quiz tomorrow over average rate of change and instantaneous rate of change, or average rate of change, slope of the secant and slope of the tangents. So this question asks, at what x value is the function continuous but not differentiable? So remember that continuous means that three things have to happen. The limit of the function has to exist. The function has to have a value at that spot, and then the limit of the function and the value of the function have to be equal. So as we look at this question here, at x equals 5, the limit as I approach from the left, the y values are approaching 1 as the x values approach 5 from the left. The y values are approaching 1 as the x values approach 5 from the right. So we can say that the limit as x approaches 5 from both sides for this p of x graph is equal to 1. So therefore the limit exists at x equals 5. The value of the function at x equals 5 is the y value when x is 5. In this case, that's 1. Quite often, if the y value is the same as the limit of the function, therefore we can say p is continuous at x equals 5 because the limit of the function as x approaches 5 equals the value of the function at 5, which was 1. Now, to be differentiable, that means something slightly different. That means that the slope of the limit of the derivative as I approach 5 from the left has to equal the limit of the derivative as I approach 5 from the right. So the limit as I approach 5 from the left of the derivative of the function, and this function is called p of x, so its derivative will be called p prime of x. As I approach 5 from the left, I'm getting slopes that are always equal to negative 1/2. Remember, slope is rise over run, and this line drops 1 over a run of 2 here. So negative 1/2 is the derivative from x equals 3 to x equals 5. Now, as I approach 5 from the right, it looks like the tangent lines here, that tangent line, this tangent line, and the next tangent line, their slopes are getting, the tangent lines are getting flatter. So the limit as I approach 5 from the right of the derivative of the function appears to be going to 0. So this is not differentiable at x equals 5 because the limit as I approach 5 from the left and the limit as I approach 5 from the right are two different, of the derivative are two different things. So I would say the x value where the function is continuous because of these conditions over here, but not differentiable because the slopes of the derivatives are not, or the slopes are not approaching the same thing from the left and to the right of 5. Would be at x equals 5. So in question number 7 then it says, well, what would be true about the graph of the derivative of p? So we kind of hinted at that a little bit in the previous question. As we go from x equals 6 to x equals 7, we see that we always have a slope of negative 1 over 2. So the derivative, as we go from 6 to 8, is going to be negative 1 over 2. So from 6 to 8, we're going to have derivative, and that's what we want on the y-axis, or the derivative now, not the y values like we had up here. We already have that graph. But from x equals 6 to x equals 8, the derivative is always negative 1/2. Now, at x equals 6, this function is not continuous, therefore it's not differentiable. So I have an open circle at 6, but at 6.1 and 6.01 and 6.001, the slope of the tangent line would be the same as the slope of the line itself, which would equal negative 1/2. Now, let's play the same game on the other two linear parts of the graph, and then we'll look at the nonlinear parts. So the linear part of another linear part of the graph is from 2 to 3, from x equals 2 to x equals 3. And on that interval, we see that the rise over the run is 2 over 1. So we'd say that the derivative from x equals 2 to x equals 3 would be positive 2 over 1. Again, the function is not continuous at 2, it's not continuous at 3, therefore it will not be differentiable at either of those spots. The slope from 3 to 5 of that line will be the same as the slope of the line. We had a rise of -1 and a run of positive 2. So from 3 to 5, we're going to have a derivative, a slope of the graph being -1/2 again. Now, as we approach, as we start at, let's look at the nonlinear parts now, here from 0 to 2. The tangent line here would have a positive slope. The tangent line here would have a positive slope, but it would be closer to 0. The tangent line, as we get closer and closer to 1, these tangent lines are going to get flatter and flatter, so their slopes are going to get closer and closer to 0. So I don't know what this graph looks like, but I do know that we're approaching 0 as we get closer and closer to x equals 1. The slopes are getting closer to 0. At 0, the function is not defined, therefore it's not continuous. At x equals 1, rather, the function is not defined, therefore it is not continuous, and therefore it's not differentiable. So we have an open circle there as well. Now as we look at values of x that are getting bigger than 1, but we have slopes that are really close to 0 as we get closer and closer to x equals 1, and the further we get away from x equals 0, the more negative those slopes become. So we can estimate that the derivative might look like this. Now if you decide that you want to make this curve down into here or curve out of here, that's fine. But we definitely don't want to have an assigned derivative at x equals 2. Now at x equals 5, we've already talked about what happens as we come in from the left. As we come in from the right, though, we see that we would have positive slopes that are getting closer and closer to 0. So at 5, we said it would be undefined. If we come in 5 from the right, we're getting closer and closer to 0, but they would be positive. And again, whether or not you make that curved or a straight line situation, that's fine. And then we'll have an open circle there. So I hope that helps with questions 6 and 7 on the worksheet. I'll post the rest of the answers to the worksheet in our Canvas page. Thanks.